Alrighty, welcome back to operating systems. Wow, that's loud. All right, so I'm here for you. What do you want to do? It is midterm eve. There's no questions whatsoever? What do we want to go over? Yeah. Page table stuff? Like one of the questions from past years? All right, page tables. Let's see. From any specific exam? Let's see. Oh, here's a new one. Oops. All right. So here's one that was the 353 final last year. So there's a virtual memory question, which should be able to do. You may have not seen this yet if you've only looked at the past midterms, but hey, the final is cumulative, so you can look at past finals and see if it is relevant. Let's see, with this one. So we created some silly machine that has a 12-bit virtual address. It's good to know, 8-bit physical address, page size of 16 bytes. If we see a page size, well, we should probably just write it in powers of 2. What's 16 in powers of 2? 2 to the 4, right? So before even reading any more, I will just put 2 to the 4 there. And we have a page table entry of a single byte. So that is how big our page table entry is. Then it says our page table entry has the following layout. So if it's a byte, that means it's 8 bits. And our page table entry looks like this. The top 4 bits are the PPN, and then the bottom 4 are just the permissions. So that's valid, read, write, and execute. And in this, we don't really use them. Yeah, we just either turn them all on or turn them all off. So this is a physical memory dump. So this tells you what every single byte is in memory. So at address 0, that's this byte. At address 7, that's this byte. If we're going at address 24, well, that's this row, and then it's sequential offset from the column. So at 24, it would be this byte here, which would be 3F, which that would be a page table entry if this is part of our page table. So it's nicely divided for you, so you don't have to write it out in binary. So here, the 3 would be part of the PPN, and then this byte, which is the 4 bits, would correspond to these bits up here, which would be all the permissions. So if it's F, it's just 111, means it's valid for everything. So any questions about this little setup that we have right here? Silly little system. Yeah.
Is there a reason we're putting the PPN at the front, or is that just like...
Yeah, so the question is there a reason we're putting the PPN at the front? Doesn't matter. Doesn't matter. You can do the page table entry however you want. Usually people put the bits at the very bottom, like the permission bits at the bottom, and PPN at the top, but I could switch it around. Doesn't matter as long as you're consistent. Yeah.
So the rows are like page tables, and the columns are like the offset or the page table entries?
So for this, the row just says like the base address, and then on the columns, that's like the offset. And this just shows you like a physical dump of memory. So these could represent page tables, they could just represent normal memory. We don't know unless we know, which one of these are page tables. So in here, well, it says our page size is 16 bytes. So how many entries could we fit on a single page? In this case, 16, right? Our page table entry is 1 byte. So we could fit 16 entries on a page in this case, which makes things a bit easier. So yeah, here we go. First question, how many bytes would we need to store a single level page table if we used it? Yeah. 2 to the 8. Right, any concerns about that? See how we got that? So how many bytes would we need to store? So we have a 12 virtual bits, and we can just essentially divide that by our offset, or minus our offset. So in this case, because our page size is 16 bytes, well, this is our total virtual memory is to the 12 bytes because we have a 12-bit virtual address. And then, well, if we use a single large page table, we would need to address every single page in there. So we need to figure out how many pages would be in virtual memory. So we just divide that by the page size, and then we get 2 to the 8 because we can do powers of 2 math. So any questions about that? And here, in this case, each page, that's how many page table entries we would need, and page table entries are only a byte, so we don't have to do anything there. Yep.
So like all you did is you found how many bits for the virtual page number, right?
Yeah, so here I pretty much figured out, yeah, how many bits for the virtual page number, and then I need that many page table entries. In this case, my page table entry is only a byte, so I don't have to do anything special. But if my page table entry was bigger, I would have to multiply. I need a page table entry for each virtual page number, right? So I would need to multiply it. But in this case, multiplying by 1, pretty simple. All right, any questions where we're at so far? So yeah, virtual memory is always a fun topic. Everyone loves virtual memory, right? Whew. All right, tough crowd. All right, so for the remaining questions, we're assuming multi-level page tables because more page tables equals more fun. So if we use multi-level page tables, we'll assume each page table fits on a physical page. And asks, what's the minimum number of levels of page tables we need in our system? So we need to figure out how many page table entries we can actually fit on a single page. So how many page table entries can we fit on a single page? 16 or 2 to the 4. So we got 2 to the 4 entries on a single page. So that would be, we would need 4 index bits to be able to select which one if we're using multi-level page tables. And then our equation is just, you know, virtual bits minus the offset bits divided by the index bits. In this case, well, from the question, we have 12 virtual bits because that's how big our virtual memory is. Our offset is 4, and our index is also 4. So if we take that and take the ceiling of that, well, luckily it divides evenly. 12 minus 4 is 8, divided by 4 is 2. So we need 2 levels of page tables for this. Yep.
But isn't the minimum number of levels just 1? Because like that's the smallest number of levels you can have.
So it's the minimum number of levels to be able to map the entire virtual address space. Because if we only had 1 level, we would only have 1 page table with 16 entries. So we could only address up to like 16 times 16 bytes, which would only be 256, which would be like 2 to the 8, right? So I can't actually address everything if I have just 1 small page table. All right. So any other questions with what we have here? That's good. We need 2 levels of page tables, and then we assume that for the rest of the questions. All right. So now we're going to translate the address 1, 2, 3, all in hex. And our highest level page table is currently at ppn 2. And remember, it takes up an entire page. So if we go back to this virtual memory, we know that, well, ppn 0 would extend from address 0 all the way to 10 here. So I'll just divide this virtual memory essentially into pages. So every page is 16 bytes. I'll start with the first 16 bytes and draw a line for every page. Yeah, let's make it look nicer. So essentially we'd have 4 pages, right? 4 pages of 16 bytes. One would start with 0 all the way to 10, then 10 all the way to 20, So any questions about just dividing that into pages? No? Okay, good. So now it says our highest level page table is currently at ppn 2. So what's our highest level page table if we have 2 levels of page tables? Is it L3? L1, right? So if we have 2 levels of page tables, it's L1 and then L0. That just contains our actual mapping for this address. So it says our highest level page table is currently at physical page number 2, and it's a page, right? So this would correspond to all the addresses from 20 all the way to 2F inclusive, or if you want to do it exclusive, it would be 20 all the way to 30 not exclusive. So in this case, that would correspond to here. So this is our L1 page table, all of these entries. If our PPN is 20, corresponds to this being our L1 page table. So any questions about that? Okay, so this is our L1 page table. Now, you can tell I was also nice here because I didn't have you write it out in binary. Everything is just 4 bits. So for this number, the most significant hex corresponds to the L1 index. The next corresponds to the L2 index. And then this 3 is just the offset because it is the least significant. And they seem to all, in this case, they're all the same size. So any questions about that? Okay, so what's the L1 index here? For virtual address 1, 2, 3. Just 1, right? Just 1 in hex. So that is our index into our L1 page table. Which byte would that correspond to here? Yeah. 0x21, because, well, our L1 page table starts at 20, and then we need to go to the first index. So this one would be index 0. This one would be at index 1. So we're essentially using the byte right here. And because this is our page table entry in our L1 page table, well, it points to what to use for the L0 page table, right? So we can check the permission bits. So in here, F is just 1, 1, 1, 1, and then the PPN is the top number. So in this case, if the valid bit is 1, it means this entry is valid, and this should correspond to a physical page number of 1 for our L0 page table. So where would our L0 page table be then? Right above it. So because the PPN was 1, that means that, well, essentially I'm using page 1 for my L0 page table. So that means this thing highlighted in cyan, I guess that's the color, that is our L0 page table we have to use. So That's what our entry in L1 told us. The entry tells us what L0 page table we need to use. So, what index do I use in the L0 page table for this virtual address? 0 or 1, 2, 3? 2. So where would that be here? What byte would that be? Yeah, so it's FF, so it should be 0, 1, and then if we have to go over into the entry at index 2, well, this is entry at index 0, 1, and 2. So this would be our entry in the L0 page table. So again, we would look at the permission bits. In this case, well, this F represents the permission bits, so they're all 1, 1, 1, so it's valid, and we're all good. And the PPN is just F. So that, because this is our L0 page table, that contains our actual mapping. So we have found the physical page number to translate from the virtual page number. So what's the other question? So what is the value of the final PTE if it was valid? Hopefully we got to that point. We were in this situation, and the value was FF, right? So the last part is, what is the resulting physical address? So again, remember we started with the virtual address, whoops. That was our virtual address. And we found what physical page number this should correspond to. So what is the actual physical address that we would resolve from 1, 2, 3? Yeah. 0xF3. Because remember, if we break up this address, well, let's just break up the hex part of it. This essentially was our virtual page number, and because we were using multi-level page tables, we broke that into 2 indexes. And here was our offset. And if we want the physical address, well, we keep the offset the same, so it's still 3, and we just substitute in the virtual page number for the physical page number. So our physical page number from the entry, because we got FF, and here the top 4 bits were the physical page number, so we just substituted in because we found it by following all the entries. So in this case, we would get F3 because that is the physical page number we found out. So if we write in hex, it is just 0xF3. Any questions about that? Yeah.
I just have a question about the overall question.
Mm-hmm.
So you divided like the physical memory into page tables.
I divided it into pages.
Yeah, but we're assuming a page table is of size page, you know? So like, but that's not the question. The question is, did you assume byte alignment in this question, or does that not matter?
Byte alignment?
Where
Or
the
like
last-
page alignment?
Yeah.
Yeah, you always assume page alignment for these. Yeah, so that was like part of it when we went through virtual memory and talked about alignment. Like it's really important that all the pages are aligned. Otherwise, it makes this math become way worse because we're essentially not doing any math because we don't have to translate the offset or anything because it's just within a page and the pages don't shift around any. If it started at just some random address that wasn't aligned, we would have to like keep track of it all the time and it would just be a pain in the butt to deal with. So this only works because everything's aligned. Yeah. Sorry? Yeah. So for why this is to the power of 8, so it's essentially saying if we use a single level page table, we need an entry for every single virtual page number, right? So this is just essentially asking, well, how many virtual page numbers do we need if we have a page size of 16 bytes and we have a 12-bit virtual address? So it's basically saying how many virtual pages do I have across all the memory. So in total, for virtual memory, I would have 2 to the 12 bytes. That's like my total accessible virtual memory. And then you just have to figure out how many pages are in that. So in this case, since my page size is 2 to the 4, that's how many pages I have. And then this tells you how many virtual page numbers there are. Right? And then to get how many bytes you would need, you would also need to multiply it here by the page table entry size, because each of those virtual page numbers would need a page table entry if we just had one gigantic table. So in this case, PTE size was 1, so we didn't really have to do anything. All right, any other questions? That was virtual memory. It's a good thing I brought this one because cough, cough. It's similar. Yeah, this is the final from 353. Winter 353, yeah, I only did 353 once so far. Are there any more virtual memory questions? So I think locking, semaphores, threads, file systems. Threading. I think the other one was fairly lame. File systems, virtual machines. No, not really. This is probably the hardest one there is. Where did it go? Yeah, this one's probably the hardest instance of it. Yep.
So, do we need to know the least recently used algorithm?
No, we haven't talked about least recently used. That's page replacement. That's next.
Do we need to know what WC is, like word count Unix command?
Not really. Yeah, you don't really need to know what WC is other than it's just a program that you can execute. You don't really care what it does. It's like ls. Yeah, it does some stuff, whatever. All right. Yep. What? No, that was yours. The midterm from CS 111? Oh, that was yours. The last, this one? So the 2 in this formula, it says, this formula says recall for the single level page table. So the 2 in this formula is because it's only a single level page table. It's the page table lookup and then the normal lookup. So specifically, I only just gave them, so this was also closed book. So I gave them this. So I said, here's the equation for a single level page table, and then I said calculate it for multi-level. So that's why it's 2 in this case, because it was specifically only for a single level. All right, anything else? Any other fun things yet?
I think this is for the same question. It says your system uses 2 megabytes, which is 2 to the 21 bytes. Yeah, it's 2 to the 21 bytes.
For this one?
Yeah.
Yeah.
So if your system uses 2 to the 21 byte pages, you need 24 offset bits, no? Because
So,
that's
for this, yeah, I need 21 offset bits.
24, no, because that's in bytes. Like that's
No,
just
this is in bytes, and memory's byte addressable. Yeah, very important to know that memory is byte addressable, so I'm not addressing individual bits, otherwise it would throw things off. All right, yeah,
Sorry, so it says your system has 2 to the power of 21 pages, but we're saying that some of them aren't going to be used for page tables, and will there like be no, like, is it going to be like, are we assuming all of them are going to be used for page tables? First,
no. So this is just like, so here I like took liberties. This is just should just say page size. So page size is 2 megabytes.
oh, page size, okay, never mind, sorry.
Yeah, that's what I meant by it. I probably was too. Why use few word? Why, you know, that's stupid me. I tried to use little words. No work did it. Yeah.
2022 final question two. Can you do that one?
2022. So the.
It was on the slides from process practice. Like,
Wait, this one?
no, it was on the slides. It's not this final. It was on like there's the process practice slides.
The
in lecture is, I think.
oh,
Like
oh,
the last 2 slides.
can you show me it quick?
Yeah.
Let's see. What we,
In this question right here. It's the same question as this one, but we use wait PID instead.
oh, okay. So we can. So we want something that looks like, come on, main int I equals 4. All right, this will be fun without syntax highlighting. All right, so we essentially have this program, and it says, essentially, what the hell does it do?
Prints 321 or not 3210.
Yeah, well, let's go through it. So we will have, you know, some original process. I usually like to start them at 100 just to make life easier. So process 100 will start executing, creates an int called I. It is equal to 4. It will be on its stack, and it will get a value of 4. Go into the while loop. Right now, I does not equal 0, so it will fork. And then create a copy of itself. So if it creates a copy of itself, we'll probably get process 101, right? So what are the difference between process 100 and 101? Yeah.
They're going to return different bits. Like the child will return pid equals 0, the parent will return pid equals 101.
Yeah, they'll have different return values from fork, and then they'll create PID and assign their different ones. So will process of 101 have a variable called x, or I? Yes. What will its value be? 4, because it's a copy of a parent. So then after, do we know what will execute next? No. So let's just assume they both just return from fork just for fun. So PID in process 100, what would that be assigned? 101. 101. What would PID be assigned in process 101? Good old goose egg, 0. Do we know which process is going to execute next? No. So I can see into the future. So if I see into the future, let's just say process 100 executes. So if process 100 executes, well, PID is not equal to 0. It would go into this else, and then it would wait. Now it's waiting on process 101, which is its child. So I'll put the process tree up here. So what would this wait call do? Yeah.
Block until the 101 dies or terminates.
Yeah, process 100 would get blocked, which means it cannot execute anymore until process 101 is terminated. It calls exit, or, well, in this case, we assume it calls exit. Maybe someone kills -9s it, but that's kind of beyond the scope. So it's stuck here. It's blocked. It can't do anything. So now process 101, well, it would continue executing. In this case, its PID is equal to 0, so it would go into this else, and it would decrement I. So it would change I from 3 to, or 4 to what? Hopefully 4 to 3, right? So it decrements its I. Is it going to affect process 100's Y, or I? No, right? Because they are independent, they are different processes, they have their own virtual memory. So in this case, process 101 just decrements it. It would go for the while loop and then go fork again. In this case, process 101, okay, it forks, so it would probably create a process called 102. In process 102, will it have a variable called I? Yes, what will the value of I be? 3, because that's what it was at the time of the fork. Trick question, will it have a variable called PID? Yes, what will the value of PID be? Of what? 0, right? So it is an exact copy at the time of the fork, and now fork returns, and then that's going to overwrite the PID in both the processes. So immediately, what is the PID going to be overwritten in process 102? What's it going to return from fork? 102. Just 0. So it's just going to rewrite 0 with 0, right? So, all right, what about 101? What's going to happen in 101? Yeah, it's going to get the value 102 and then overwrite its value of PID. So now what's going to happen? Well, in this case, I know that process 101, because its value of PID is not equal to 0, it's going to go and hit this wait call. So let's say process 101 executes. It would eventually hit this wait PID. So it's going to wait on process 102. What does that mean? It's blocked. So process 101 is now blocked, waiting on process 102 to terminate. So process 100 and 101 are both blocked. And now process 102 can go ahead, decrement I from decrement I from 3 to 2, and then it would go back up for this while loop and then fork again. And then it's going to get kind of boring. So it would create process 103, and then it's essentially going to be the same thing. So it would overwrite fork, or PID from fork, it would get 103. Then we would have process 103 has I equal to 2 and PID equal to 0, assuming, you know, it just returns from fork. So then in this case, well, if process 102 executes, it would getting crowded at that wait call. So now it's going to wait on process 103 to execute, and it can't do anything at all. So after that, do we need to go through the excruciating detail, or can we skip some steps? Let's skip some steps. Okay, so 103 is going to create 104. Whoops. So that creates 104. In process 104, I would be equal to 2, PID would be equal to 0. Process 103 is going to hit that wait. It's going to wait on process 104. And then in 104, well, we're going to decrement I all the way, whoops, we're going to decrement I to 1. And then go through, in this case, I is still not equal to 0. So 104 is going to create 105. And then in 105, I would be equal to 1. PID would be equal to 0. And this, well, would be go to this wait call. All right, so I think I have adequately skipped a number of steps. So let's just make sure we're on the same page. So at this point, I will have process 100, 101, 102, 103, 104, all at this wait PID call, waiting on its direct child. So any questions about that? Yeah. Sorry? In 103? Yeah. Whoops, I skipped a step. I went too fast. Sorry, you're saying it should be this, 105 shouldn't exist. That? Okay, oops, skipped too many steps. All right, so process 100, 101, 102, and 103 are all that wait call, and now I have this process 104, which is essentially right here at this point. All right, so any questions about that? We're all waiting on each other, and process 105 doesn't exist. So now, at this point, what's the only process I can actually execute? Hopefully 104, right? Because all the rest of them are blocked on that wait PID call. So if 104 executes, well, it would hit here, it would check this while, in this case, I is equal to 0, so it would just hit here and hit return. What's returning from main the exact same as doing? Exiting, right? So exiting was 0. So now is process 104 donezo? Yeah, so 104 is donezo, so that means this is dead. At this exact moment, what is the state of process 104? Is it a zombie, is it an orphan, or is it just chilling? Technically a zombie, right? So we haven't completed the wait call yet. So trick question, that's why I said at this exact moment, because it's quickly going to be cleaned up. It's not going to be a zombie for very long. So 104 is terminated, not cleaned up. So if we unblock process 103, then that means we completely clean up process 104. So 103 would wake up and then print. What would it print? 1. So it would just print out 1, and that's the only thing that could have executed. There's no other order that could have happened because all the other processes were blocked, right? There's no way I could have printed 4 at this point. So now, well, this would print 1 and then immediately exit. So if 103 exits, it's now terminated. It is temporarily a zombie, but now that will unblock 102. And if 102 executes, well, it returns from its wait, and what would it print? 2. And then it would go ahead and exit, and then 102 would wake up, and 102 finishes, and then 101 can wake up. It's going to print, in this case, 3, and we have no other choice. Then 101 is going to exit. And then if we unblock process 100, well, then we clean up process 101, and then process 100 will just print out 4, and then terminate, and we're done. So we have to print in the order 1, 2, 3, 4. There's no other choice because of that wait call. So I could have executed the child programs first if I wanted to, but wouldn't have made a difference. We got the same result anyways. So any questions about that? Nope. Okay, so something that I'm really bad about keeping secrets about exams if you ask me questions. So let's see how much I say. All right, so here's this question, which is like technically valid. So this is processes and threads, and it doesn't have anything to do with databases or anything. This would be valid to ask you. I also have a bad short-term memory, so that actually goes in my favor. So I did not ask you something this complicated. I asked you something about threads, but I forget what. It was definitely a short answer question. So, unless my memory is really bad, I don't think it's that bad. But in this case, we could actually answer this question. So this just has to do with forking and making new processes. So at the beginning of this, let's see how good we are. So let's say process 101 starts executing main and calls fork immediately. So what's that going to do? Yeah, create process probably 101, and it's going to be exact clone, and we're going to have 2 processes here that want to start executing after the fork, right? So now 2 processes that are otherwise the same. The only difference is the value of PID. In 101, PID equals, or 100, PID equals 101, and 101 PID is equal to 0. So in this case, we have no idea which one is going to execute first. Say 100 executes first. They're independent at this point. It creates 2 threads. So we have the main thread and then 2 other threads that want to execute this run, one with the value of 1, one with the value of 2. At this point, do I know which of these threads is going to execute first? No idea. I have no idea. Well, after I make it, I have no idea if the main thread is going to execute next or whatever, but the main thread would hit join, so it has to wait for thread 1 to actually finish before that join happens. But I don't know in what order anything is going to happen in. So what could happen is I would have thread 1 here, thread 2, and these would be from process 100, so I'll just put 100 under them. And they would get their value from arg. So thread ID for thread 1 would be 1, thread ID for thread 2 would be 2. And then they fork. Anyone remember what happens if a thread calls fork? Yeah. Yeah, it'll just create a new process that's a clone of whatever the thread is that called fork. So in this case, this was in process 100, so this fork probably made process, here I'll draw the tree up here. Oops. So process 100, probably this thread would have made a process called 102 or something. That is a child of process 100. And 102 that process 102 only has a single thread in it, right? Which is a copy of, in this case, which thread did I say called that fork? Thread 2? Yeah, sure, thread 2. So thread 2 called that fork. So in process 102, well, it's only going to have a single thread, and it's going to be a copy of thread 2. So in process 102, I can just shorthand it because now it only has a single thread in it. Well, it would have a thread ID equal to 2 because it's a clone of whoever called it. So it had thread ID equal to 2. So in this case, I don't know which of these is going to execute. Let's say process 100 runs, let's say. So in that case, I would have a print that says thread 2 run in 100, something like that. That could happen. And then we would move this. It would check if PID is equal to greater than 0. In this case, thread 2 created that process 102. So it would have had a PID equal to 102. And here PID would have been equal to 0. So it would wait on process 102 to finish after it actually printed. So that would wait. If process 102 executed, well, what would it print? So yeah, if 102 executed, it would print thread 2 running in process what? 102, right? How much time do we have? We don't have that much time. So we've processed thread 2 running in 102, and then it would eventually check its PID. It's equal to 0, so it would hit return null. So for a thread, what is returning from the thread function the same as? Not quite, yeah. Yeah, pthread exit. So it's a dual for thread. So if you return from main, that's the same as calling exit. If a thread returns from its thread function, that's the same as calling pthread exit. So in this case, in process 102, well, because we forked it, there's only one thread in that process. So if it calls pthread exit, similar to your threading library, if it's the only thread that's in the process, it just ends the process because there's nothing left to execute. So in that case, process 102 would be terminated, and then thread 2 and process 100 could get unblocked at this point. And then return, it would return null, and then that thread would exit, thread 2 would exit in process 100. And then in process 100, it could pass this join and go ahead and start waiting on, it couldn't because, sorry, the first join is on thread 1. So thread 2 is terminated, but this join is on thread 1, so it wouldn't make any progress yet. So the main thread's still blocked on thread 1. So eventually, yeah, so any questions about this in the last like 2 minutes, because I don't think I have more time to go through it. Yeah.
So it's just gonna run, it's just gonna print thread 1, thread 2 running in whichever process, but you don't know the order, do you?
Yeah, you have no idea. So eventually, in this case, thread 1 running, so that would also create a new process, so probably in 103. Thread 1 run in 100, something like that. But in this case, there's no ordering on them. You have no idea which one's going to order because the wait happens after the print statement. So there's going to be no ordering whatsoever. Yeah. Yeah, so because I fork in main immediately, process 101 will do the exact same thing. So it will create 2 threads, and then 2 of its threads will go ahead and create 2 new processes. So eventually, solution should be on it. So this would be like my total process tree. So this would get created from thread 1, thread 2, thread 1, thread 2 in their associated parent processes, and I would see essentially this. But this is just an ordering, so there's actually no ordering whatsoever. All right, we're good? All right, so also on Wednesday, during the practical hours, depending on whenever I get to Toronto, if there's a lot of people there in demand, I might show up there and answer any like super last minute questions. But with that, just remember, pulling for you. We're on this together.